So now that we've defined the exponential function, exp of x is the inverse function, which some people would write natural log inverse, -1 of x. This allows us to define what an exponent means for any real number, not just the rational numbers like I talked about last time. So what does that mean for us? Well, let's actually define it. So we'll define, and we'll have to limit ourselves to positive values of a here. We'll define a to the x to be the exponential function of x times the natural log of a. Now, what does that do for us? Well, it does a couple of things. First of all, we know this will make sense for e to the x, because e to the x should be the inverse of the natural log. So and remember, we defined e to be the exponential function evaluated at 1. We'll learn later in the course that that's about 2.7. E to the x would equal the exponential function of x times the natural log of e, and e is the exponential function evaluated at 1. Now remember, just a moment ago, I said that the exponential function is the inverse of the natural log. That means these will cancel each other out. And that means that what am I left with? E to the x is the exponential function of x times 1, which is just x. So that means that this exponential function, as I promised you, is exactly the same thing as e to the x. Therefore, we get our nice properties that the derivative of e to the x is itself, and the integral of e to the x is itself plus c. So that's, and we can actually prove those properties now using this rigorous definition of the natural log, which involves the integral of 1 over x. Let's do another example of a problem that we can do now. You might think it's very weird that I defined the exponential function and didn't talk anything about multiplying things over and over again. So let's make sure that that still matches up. So, as I often do, if I'm asking you to use a definition, I'll remind you of what that definition is. Use the definition. A to the x equals exponential function of x times the natural log of the base a, and the property the natural log of a times b times c is the natural log of a plus the natural log of b plus the natural log of c. And that's a property I proved in an earlier video for a and x. And it's not too hard to do it for 3 things as well. And so I'm going to use that definition of that property. What am I going to do with it? I want to use it to show that 2 to the 3rd power, using this very silly, well, at least it looks silly, right, definition, but it actually does what it's supposed to do. 2 to the 3rd power is 2 times 2 times 2. So it should be 8, of course. So let's make sure that that actually matches up. And if it doesn't match up, then I've done something terribly wrong. But I think it'll be all right. So what am I doing? I'm going to use, I have a to the x. I'm just going to let my a equal 2. And I'm going to let my x equal 3. Okay? So a equals 2 and x is equal to 3, and that's going to get me my definition. So 2 to the 3rd power equals the exponential function of x, which is 3, times the natural log of a, which is 2. Okay. Well, that's all right. Now what do I do here? Well, I've got to use the fact that I can talk about the natural log of a plus the natural log of b plus yada yada. Well, that's basically what I have, isn't it? I've got 3 natural logs of 2, so that's going to be the same thing as the natural log of 2 plus the natural log of 2 plus the natural log of 2. All right. So here I've got a different a, b, and c. I've got 2's here, here, and here. And so what is a times b times c? That's a big ol' 8. So what can I do now? Well, that's just the exponential function of the natural log of 8. And those are inverse functions. Exponential functions and natural log functions, this is exactly the same thing. You might prefer, because this is the way you thought of it, you might also think of this as e raised to the natural log of 8 power. Either way you think of it, they cancel, and I'm left with just the number 8. 2 to the third is 8, and 8, of course, as we know, is 2 times 2 times 2. And that finishes the proof right there for us. So, even though it's a weird-looking definition, and we need that because if we're not dealing with nice numbers like 2 and 3, we have to have it make sense for those numbers too. But it does make sense for the usual numbers, and it does work out. You can prove in general that this exponentiating definition, it just means multiplying by itself over and over again as usual. So now we have the idea of what raising an exponent is for all real numbers. We can also define logarithms for different bases. So this is up here, a to the x. We might even give this a name. We might call this the general exponentiation function. As opposed to the natural exponentiation function, which is just e to the x. In general, a could be any positive number. And we can also define a general logarithm. That means a logarithm which doesn't have a base of the natural number e. And so what's that going to be? Well, we've got a log base b of x, and the way we actually define it is just by taking the natural log of x and dividing it by the natural log of b. And this is only going to make sense again if the base is bigger than 1. And the idea there is, well, it has to be positive because we have to plug it into a natural logarithm, and it can't give us a 0, so it can't equal 1. That would give us a 0 in our denominator, and we don't want that. Okay, so that's how I'll define that general logarithm. I can solve problems with it as well. I'm going to use the definitions. So a general logarithm is you just receive that by dividing the natural logarithms. That's one definition, and I called it a to the x earlier, but it'll be useful to use it in terms of b instead. In general, b to the x is rigorously defined to be exponential function, x natural log a, and I'm going to prove the property that log base b of b to the x is just x. And what does that mean? Well, really that just means that they are inverse functions of each other. Just like the natural log is the inverse function of e to the x, the log base b is the inverse of b to the x. And we can do that from these definitions beyond a shadow of the doubt. So what do I need to do here? Well, I'm going to apply all these different definitions. I'm going to start with the left-hand side. Log base b of b to the x. And I've got a nice definition of log base b of regular x. So I'll just use that. Natural log of, well, instead of regular x, I have b to the x divided by the natural log of just b. That b here has to do with this b here. It's the same as this b down here. That's not different. The only thing that's different is the x's. We have an x here, but down here we have b to the x. So we have to have a b to the x on the top. Okay, well, let's move this forward. I also need to remember that b to the x, I have another definition for that. And this is a lot of these problems. If I'm going to ask you to prove something, most of the time it's going to be, hey, just plug in for all your definitions and it'll just pop right out. And sure enough, b to the x, we can replace that with the exponential function, exp, of x natural log of, and I apologize, a moment ago that was supposed to be a b up here, natural log of b, because in that definition I replaced all my a's with b's. And then we'll divide that by the natural log of b. Alright, good news. Natural log and the exponential function cancel each other out. So what am I left with? I'm left with x times the natural log of b divided by the natural log of b, cancel, cancel. And that finishes the proof. And that lets us have a general logarithm and a general exponential function. They have the properties that they're supposed to, but now they've been defined rigorously using integrals.